All right, continuing on with section 1.3. Every tree, the next theorem 1.3.4, every tree with at least one edge has at least two end vertices. That is vertices of degree 1. Right, we already basically have proven this one twice. So if you just look back at the proof of theorem 1.3.1 and 1.3.3, right, we use that technique twice. If you have a tree with at least one edge and it has two end vertices, just take the longest path right in there, and then the longest path, right? It has to have the ends have to be degree 1, because if not, then you could make the path longer, but it's the longest path, right? And then or the other thing is that you would make a cycle in there, and a tree can't have any cycles. So we basically already proven this one twice. So here I just want to note, right, that uh, we've again proven this one in the proof of 1.31 and 1.33. All right, that brings us to 1.35. And that is a graph G is a tree if and only if there exists exactly one path between any two vertices. All right, so that's the next one we want to prove. All right, so the first direction is that if G is a tree, then there exists exactly one path between two vertices, any two. Okay, so let G be a tree, and suppose suppose G is a tree and there exists vertices A and B, and of G, and two distinct paths, AB paths. And I'll call one P1 and the other P2. Okay, so they are different paths, right? P1 and P2 are distinct paths. So that means that there is a vertex that belongs to both path 1 and path 2. Right? Such that the vertex after that common vertex is different in P1 and P2. All right, so picture wise, it's going to look like this. So we have P1 and P2, they are leaving A, right? And they might follow the same path for a while, but then at some point, since they are different paths, right, they're going to have to take a different route to get to B. All right. And so that vertex U right there, the one right before they split out, somewhere along the line, I'm going to call that one U. Okay. All right, so U is in both P1 and P2, but the next vertex after U is different in P1 and P2. Okay. All right, and so that has to happen in order for these to be different. It could happen at A, right? It could happen really almost anywhere along the line here, but it has to happen someplace. Okay. So there exists a U such that U is in both P1 and P2 and different than the other. Okay. All right. So then after that, right, there has to be some vertex W in P1 and P2. Okay, so after a while, because we know these paths, draw B right here, we know that these paths have to both meet at B, right? And so I'm going to follow, say, path 1, right? And then somewhere along path 1, there's going to be some vertex after the one after U where the paths come back together again. And that first vertex after that, after where they split apart, where it comes back together, I'm going to call that W, right? And so it's going to look something like that. Although there may be a lot more vertices between U and W on both P1 and P2. All right, so there is W in P1 and P2, right, where W is the first vertex in P1 after U that is in also in P2. So where they come back together. Okay? And so that's the idea. So basically, right, if you draw what P1 is going to look like, P1, right, would look like this. It would start at A, right, and then it would go along. And then somewhere along the line, right, after it starts off at A, it hits this vertex U, right? There are going to be some vertices that follow it. All of these are in P1, right? And then comes that vertex W. Remember that vertex W, right, is the first vertex after U where these that's also in the path P2, okay? And then after W, it's going to continue on and eventually wind up at B, okay? All right, and then P2 starts at A, it goes along, right, and shares these possibly in common with U, and then that's where it splits apart, right? And so it splits apart, and you've got some you've got some vertices, and these vertices, right, are only on P2. They are not on P1, right? Because otherwise, then W wouldn't be the first one in P1 that's not also in P2, right? It would be further along here. And then P2 will continue on, eventually making its way to B, okay? So that's what P1 and P2 look like. All right, and so then you can already see, right, where we're headed probably here is that we're making a little cycle. And if we make a cycle, right, that's going to contradict the fact that there exist vertices A and B with two distinct paths in there, okay? And so, so what is our cycle? Our cycle would be U, V1, V2, right, all the way out to Vm. And then we would have that W, and then we would just follow this path back, right? So we would have Yn, right, Yn minus 1, all the way down to Y2, Y1, and then we would arrive back at U, right? So we're going this way and this way, and that is a cycle, right? Okay, and so, right, that contradicts, right, the fact, this assumption, right, that there exists vertices A and B with two distinct paths between the two, okay? So that is a contradiction. All right, so next direction, right, that we have to prove is that if there is exactly one path between any two vertices, then G is a tree. All right, so how that direction would go, right, is that just the fact that there is a path between any two vertices So since there is a path between two vertices, G is connected. Okay, so that's right off the bat. Okay. Next up, right, is suppose that G is not a tree, right? So if G is not a tree, then G contains a cycle. Okay? So G is not a tree. That means G contains a cycle. Well, if you have a cycle, right, then there is, if you take any two vertices on that cycle, there's two distinct paths between the cycle, right? We talked about that in the proof of theorem 1 point, or the, actually I think it was the proof that every walk contains a path, right? So that would mean that there exists an A and a B in G with more than one path, that A and B being on the cycle that G contains. So more than one AB path, and that is a contradiction. Okay. So that contradicts the fact, right, that there's exactly one path between any two vertices. Okay. All right. So, and that is the proof of the other direction, right? So we have established, right, a graph G is a tree if and only if there exists exactly one path between any two vertices.